Good day, students. Welcome to Mathgotserved.com, where we don't just solve, we teach. In this clip, we're going to be going over problems 21 to 24 of the January 2016 Geometry Common Core New York Regents exam. All right, number 21 reads, in the diagram below, segment DC, AC, DOB, CB, and AB are chords of circle O. Line FDE is a tangent at the point D, and radius AO is drawn. Sam decides to apply this theorem to the diagram. An angle inscribed in a semicircle is a right angle. Which angle is Sam referring to? That's the question. So there is a theorem that you might want to recall to help you solve this problem, which is known as Thales theorem, which basically states that the inscribed angle subtended by the diameter is 90 degrees. Okay, so in this problem, what our focus is on the inscribed angles. Okay, so where are the inscribed angles that we have? This is an inscribed angle right here. We have an inscribed angle right here, an inscribed angle right here, and an inscribed angle right here, and another inscribed angle right there. Okay, well, one of them is related to the semicircle. Now, what is a semicircle? Semicircle just basically means half the circle. Okay, so which of the inscribed angles subtends half the circle? If you look at all the chords that we have here, only one, namely the diameter, that's the chord that divides the circle into two congruent halves, namely semicircles. Okay, so this entire section is a semicircle, for instance, and then do you see the angle that subtends this arc right here? The inscribed angle that subtends that is that angle right there. Okay, now let's go back and take a look at Thales theorem real quick just for confirmation. According to Thales theorem, the inscribed angle that subtends the diameter, so this is the diameter, and this is the inscribed angle right here. Guess what? That angle, angle C, is equal to 90 degrees. Okay, so the angle that what's his name? Sam is referring to is this angle right here, because this angle is an inscribed angle in a semicircle, and is also the angle that subtends that's subtended by the diameter. Okay, so the measure of angle C is 30. Let's go ahead and label it using these information here. We can call it angle DCB. So measure of angle DCB using the information provided here is equal to 90 degrees. So our answer is option number 3. Okay, let's take a look at problem 22. It says, in the diagram below, segment CD is the altitude drawn to the hypotenuse AB of the right triangle ABC. Question, which lengths would not produce an altitude that measures 6 root 2? Now, when you see a triangle, a right triangle with this configuration, and the focus is on the altitude, you want to recollect the altitude rule. Okay, the altitude rule is as follows. Let's say this is H, the altitude of the right triangle, and this is X and Y, the side that this altitude divides. The altitude rule basically states that altitude H is the square root of the product of these two sides, X times Y. Okay, so that's the altitude rule for you. So this is basically the formula that we're going to be using to figure out what the solution to this problem is. Okay. Okay, so let's note that AD is X, segment AD is X, and DB is what? DB is Y. All right, and then CD is our altitude, which is basically H. Okay, so which will not produce an altitude that measures H? So H is expected to be 6 root 2. Okay, so what we're going to do is we're going to take the different options that are provided here and use it to see if it satisfies this equation and produces a result of 6 root 2. Let's start with option number 1. AD is 2, so X is 2. DB is 36, sorry, so Y equals 36. So H is basically the square root of the product of these two segments, 2 times 36. The question is, if I simplify this, do I end up with 6 root 2? Okay, so let's go ahead and break this down. If you multiply together, you're going to end up with the square root of 72. Okay, and then you have to break it down to see if you get 6 root 2. Now, if you look at 2 root 36, you can clearly see that this 36, you can root it, and then you get 6 root 2. Okay, so just by examination of this piece, you see a 6 root 2. But let's just assume that we weren't paying attention to the fact that this can be reduced to 6 root 2. And we have our 72. We can just break it down. So take out 2. 2 goes into 72 36 times. 2 goes into 36 18 times. 2 goes into 18 9 times. And they have 3 3. And then when you're simplifying radicals, any factor that repeats, you just root them and they come out as 1. So the square root of 3 times 3, these two come out as 3. Square root of 2 times 2, that comes out as 2. And you're left with 2 as a radicand. It doesn't have a partner to break out with. Okay, so the square root of 72 is 2. This 2 comes out, times this 3 comes out, and then this 2 over here stays behind as a radical since it doesn't have a repeated factor. Okay, so it becomes 6 root 2. Is that the expected altitude? The answer is yes, so this checks. Remember, we're looking for the altitude that does not produce 6 root 2. Okay, now let's go ahead and test option number 2. We move this work to the left. Now for option 2, we are going to see if our X and Y measures satisfy the altitude rule. Okay, so for section 2, we have AD is 3. So AD is 3. So since AD is 3, that follows that X, because X is 80, okay, so X is 3. We are provided with AB. AB is 24. So if AB is 24, can we use this information to figure out what DB is? Because DB is Y. Okay, so let's go back and take a look at our diagram here. AD is 3, so this side length here is 3. And the entire length from A all the way to B is 24. Okay, so the entire segment is 24 and a portion of it is 3. Then the remaining portion, DB, has to be what? DB is going to be 24 minus 3 using the segment addition postulate. Okay, so DB is basically the entire length AB minus section AD. So we have 24 minus 3. 24 minus 3, which is what? 24 minus 3 is 21. Perfect. So since DB is 21, so what? Since DB is 21, this follows that Y is 21. Okay? Perfect. Now we have the two values we want to use to test our altitude rule. The altitude H must be equal to the geometric mean of the base that the hypotenuse, the altitude divides, sorry, basically x times what, square root of x times y. So let's plug in the x and y values from option 2 and see if we get 6 root 2. Okay, so we have the square root of x is 3 times 21. Okay, so this becomes the square root of 63. If I break this down, do I end up with 6 root 2? That's the question. Well, let's go ahead and break it down. So we can take out a 3. 3 goes into 63 21 times. Can I take out another prime factor? Yeah, we can take out another 3. We're left with 7. So these two 3's repeat, so they can be rooted out. The square root of 3 times 3 is just 3. So this tells us that root 63 is 3. Now this 7 doesn't have a repeated factor, so it stays as radicand. 3 root 7. Is this the desired altitude value? The answer is no. Remember, we're looking for which one does not produce 6 root 2. Is this 6 root 2? No. So this does not produce 6 root 2. Our answer is option number 2. All right, let's take a look at number 23. It reads, a designer needs to create perfectly circular necklaces. The necklaces each need to have a radius of 10 centimeters. What is the largest number of necklaces that can be made from a 1000 centimeters wire? Okay, so when just something to note concerning forming circles is that if a segment is bent to form a circle of radius r, then the length of that segment is going to be 2 pi r, or the circumference of the circle. Okay, so let me just illustrate what I'm talking about here. So let's say we have a segment. Let's put the segment down first. Let's say we have a segment, and this segment is a piece of wire. Okay, it was bent to form a nearly perfect circle. Okay, so this wire was bent to form this circle right here. So what this point to note is saying is that the length of this wire from this end to this end is the same thing as the distance around the circle. Okay, all the way around. Because what happened is that this wire was bent around, and then you just connect the two ends, and you have a nice little circle there. Okay. Now, if the radius of this circle that is created from this segment is r, then the distance around this circle is the circumference, which is 2 pi r, and that is equal to the length of the wire that is used to create the circle. Okay, so that will be 2 pi r also. So you want to keep this point in mind. Now let's go ahead and write down some formulas that will help us to solve this problem. We're going to be writing down some formulas concerning materials. Okay, so formulas, put it right here. Okay, so we have a certain number of necklaces, a certain number of material for wires, and also a number of the length of each wire that we are going to be using to create each piece of that necklace. So the first formula we need is the basic one that we have here. Circumference of a circle is equal to 2 pi r, and that is also going to be equal to the length of each wire. And then we also have the formula, the number of necklaces is basically equal to the total length of wire, the entire length, total length of wire divided by what? We take the total length of wire divided by the length of each necklace. Length of each necklace. They're all of equal measure, each necklace. Okay? All right, so let's fill in the values. We're going to start with the total length. So what is the total length of the wire, of the entire wire? The total length of the entire wire is 1000 centimeters, right? So it's 1000 centimeters. What is the length of each wire? Length of each wire for each necklace. So of course we're going to be breaking down this entire length, okay? So how do we compute this? We know that the radius of each necklace is 10 centimeters, okay? The radius of each necklace is 10 centimeters, and we know that the circumference of each necklace is equal to the length of the wire that's used to make that necklace. All right, so we're going to be using this formula right here. The length of each necklace is basically the circumference of the necklace, which is 2 pi r, okay? And it's going to be 2 pi times the radius of each necklace, which is 10, and 20 pi centimeters is the length of each wire, which is basically the circumference of each necklace, okay? So how many necklaces can we make? We have 1,000 centimeters of wire, and each necklace we're going to be using 25 centimeters to make each necklace. So to finish it off, we're going to use this formula that we wrote up here. Okay. So the number of necklaces is going to be the total length, which is 1,000, divided by the length of each individual necklace, which is the circumference. The length of each wire, which is the circumference of each necklace, which is 20 pi. Let's go ahead and use our calculator to solve this. So we have 1,000 entire length divided by the length of each wire, 20 pi, which is equal to the circumference of each necklace. Enter, we get 15.9. Okay, so 15.91. If you take a look at the options right here, we have 15 and we have 16. Which of these options is the correct one? Are we going to have to round up here or round down? The answer is going to be option number 1. Well, why is that the case? That's the case because we have enough material to do 15 complete necklaces. 0.9 is not long enough to complete the 16th necklace. So it's impossible to make the last necklace. So in this case, you have to round down because you are actually creating materials from the measures that you have. So you're going to round down, truncate the decimal components to 15 complete necklaces that can be made using the material that we're provided. We do not have enough material to make the 16th one. That's what this decimal component is. So we can't round it up because that's not complete. We have to round down, and that takes us to option number